We just recently, we've been sort of futzing around with our name of our company, so I just like, we think we've come to some clarity on it. We're back to Numenta. That's the name of our company, Numenta. And we have this mission, which is to be a catalyst for machine intelligence. And you all know that catalyst means accelerates a reaction that's going to happen anyway, but and doesn't get consumed in the reaction. And so machine intelligence is going to happen, and we're just trying to accelerate it as much as we can. We got three things we do. We got a research team, me and a couple other guys. We do theory and algorithms. We have an open source community, which Matt Taylor runs. And we started last summer. It's going great. We've taken the algorithms as we develop and put them into that. And then we have a business, which is a product called Grok, which we're going to launch it officially in a couple weeks. It's really cool. It's built on these algorithms. I'm not going to talk about that tonight at all. Although later, if you want to see it, I'll demonstrate. I'll show it to you. It's really cool. But I'm just going to talk about some of the research topics. That's what this is all about, and hopefully you're all here for that. Was that clear for everybody? Right? Yeah. Okay. You know, when we started Numenta, we had this big debate. Well, it wasn't much of a debate, but we thought about it a lot, which was, can you really try to understand how the cortex works without focusing on the entire motor experience as well? Can you do a purely sensory inference? Can you make progress with sensory inference without understanding how the motor interaction works? And we were not certain of that, and we went down that path, and it turned out we could, but now we're coming back to the motor side, and we've been thinking about it a lot. Okay, so that's the introduction to the talk. Unless there's any questions, I'll just delve right into it. So this is the problem. What are the problem we're trying to solve? It's, you know, it goes by different names: sensory motor integration, sensory motor contingencies. People spell it different ways: sensory motor, embodied AI, symbol grounding. Basically, is that the fact that, you know, most of the changes on your sensory organs, your ears and your eyes and your skin and others, are due to your own actions. Most of it are due to your own actions. And so it's kind of hard to separate that out. And so our model of the world, as we build from our data stream, has to take advantage, take cognizant of our behaviors. So it's we build a sensory motor model of the world, how our sensory patterns change as we interact with the world. And the questions we'd want to know are, how does the cortex learn this sensory motor model of the world? And then how does the cortex generate behavior? So those are the two topics I'll be talking about a lot here today. I have a couple of overview slides. These are just two of them. And so if you know our work, this will be not new to you, but it's worth stating again. I find it's worth stating this again. We have an overall theory about how the neocortex works. It's a very, very high level conceptual idea. We call hierarchical temporal memory. I talked about this in my book on intelligence, although I didn't use those words for it, but all the features were there. And so you have, what is it? You got a bunch of sensory data. You know, the retina is really like a million sensors. It's not a sense, it's a million sensors. There's a million fibers on it. There's 30,000 on the cochlea from the auditory nerve, and the somatic sensors are about another million bits coming in. So this data streams into the cortex. We'll talk about the rest of the brain in a moment. And in the cortex, it's built as a hierarchy. It's a hierarchy of cortical regions. These regions all do basically, they all have a very, I'll say they do all the same thing. There's variations to it, but they basically are all doing the same thing. And there's much things that are common across the species and across modalities. So vision and hearing look very, very similar, and touch and so on, and across, you know, mice, rats, and so on. The second thing is that the regions are mostly sequence memory. That's where the temporal part comes from. And the argument for this is that most inference, almost all, I'd say 90% of inference of pattern recognition is time-based. So if you want to understand my speech or any auditory sound, it's patterns in time. And the order matters, and you have to have memories of what those words sound like and the patterns go and so on. And that's true for touch as well. And it's even true for vision, even though we can do some visual inference without time, but most of it involves time. And of course, anything that cortex generates in a motor behavior is going to be sequences too. That's temporal memory, because I'm playing back recorded sequences or memorized sequences right now as I'm speaking to you. So, and if all regions in the neocortex are doing the same thing, then all regions are doing inference and motor behavior, which we know is pretty much true. So a large part of the memory in these regions is doing sequence memory. The other thing that's part of this hierarchical temporal memory theory is that as you go up the hierarchy, it's very well known that you build representations. The cells are becoming more stable over time, and they represent larger parts of the input space. So as you go forward, you're basically, one way to look at it, if you think of each level in the hierarchy, each region is sort of learning sequences like melodies, then you have to form a stable representation for any pattern, like any melody that you know, and then it's sequences of sequences and so on. So as you build up the hierarchy, you end up with cells that stay on for very long periods of time over learned experiences. And then going backwards, it unfolds. So you can take a fairly high-level concept, and then it unfolds into a series of sequences, and those unfold into a series of elements, and so on. It's just exactly what my speech is right now. Like I start thinking, oh, what's the first slide I'm going to do, and then all of a sudden I produce, that 10,000 muscle movements to say what that is. So you got this unfolding of sequences going up and down. That's basic hierarchical temporal memory. We have a theory about what a layer of cells is doing in the neocortex. That's the cortical learning algorithm, or CLA. I'm not going to say how it works. This is what's in our open source repository. This is what we've been testing for 4 years. We understand it extremely well now, and I think it has actually has a lot to do with how the brain really does this stuff. I'll just say some of the attributes to it. Basically what it does is it takes, this is representing a layer of cells, and we'll talk about layers in a moment, a layer of cells in the cortex. It takes an input to it. There's a distributed input. It turns it into a sparse distributed representation in column space. It then learns sequences of those or transitions in time, and it makes predictions and detects anomalies. It's got some nice desirable attributes. It's an online learning system, so it learns continuously. It has a very large capacity, even if it's very small. We do typical models of 2,048 mini columns and 64,000 cells, and it can learn millions of transitions. It's very high capacity. It runs high order sequences. It's built on simple local learning rules, and it's fault tolerant everywhere. So those are some nice things about it. Okay, so now we're going to jump into cortex and behavior. Here's a sort of a big picture thing you kind of need to know. So starting off with, it's worth mentioning that we have a lot more senses than the 3 big ones you think about. And I threw in here the vestibular, which is your sense of balance, and your proprioceptive sense, which is you have sensors which tell you the position of joints and things like that in your body. There's a lot of data coming in from your sensory stream. And first thing it goes to is not to the cortex, but almost all of it goes someplace else. In fact, we all have what you might call an old brain. It consists of the spinal cord, the brainstem, basal ganglia, superior colliculus, and other things like that. It's built of neurons, of course, and so this sensory data goes to various different sections of the old brain, and those things generate behavior. We all have a lot of built-in innate behaviors that don't require a neocortex, don't require the big thing on top. You can think of it sort of like a reptile brain. So that exists, and those behaviors exist. And then what happened was the neocortex came along sort of in evolutionary time fairly recently. And what happens is the following. It gets a copy. In fact, literally, the axons which are projecting to these old brains, they split. It's the same axon, and they go to the neocortex. This was observed over 100 years ago by Cajal. And this is pretty much a universal rule. So the cortex gets a copy of the exact same data which is going to the old brain. The next thing is that here's another pretty much universal rule, is that these cells that are in the old brain sections that are generating some sort of behavior, they also split, and they send the copy also to the cortex. So the cortex is getting a copy of motor commands. It doesn't know that they're motor commands, it's just actions and firings themselves. But it's not just getting sensory data, it's getting basically a representation of all the other behaviors that are being generated elsewhere in the brain. And then the final thing that happens is that the cortex itself has projections which generate behavior. They don't go right to the muscles. They go to these old brain sections. And so I drew the dotted line because it's like an influence. It's trying to influence the stuff that's already existing. So just to give you a few flavors of this, like my breathing and your breathing is pretty much, brainstem stuff. But my cortex can control it. It's learned how to do that. But it's not like it's replacing the brainstem. In fact, most of the time the cortex is not involved at all. But if I told you, hey, I want you to breathe right now, in, out, hold your breath, you'll do that. And if I tell you to hold your breath for too long, the old brain stuff takes over and says, screw you, cortex, I'm going to breathe anyway. So this is true for everything, like walking and grasping and all these reflex things. You have a lot of behaviors which are subcortical, which the cortex basically learns to control them. And this is the way the whole nervous system is structured this way. It's sort of layers on layers on layers, where the new thing sort of interacts with the old thing, the next one interacts with that, and so on. So this is the system we have to understand. It's not like, oh, the brain's just doing stuff. It's in this context. So this is just a repeat of what I just said. The old brain has complex behaviors. The cortex evolved on top. The cortex receives both sensory data and copies of the motor command. So the cortex has the information needed to do sensory motor inference. And the cortex is able to influence the old brain. Therefore, it has the connections needed to generate goal-oriented behavior. So now we'll just go into some more detail. Here's a picture of, I just made a little drawing of like a region of the cortex. And remember, the cortex is really thin. The cell's only about 2.5 millimeters thick, and the whole neocortex of a human is about 1,000 square centimeters. 1,000 square centimeters. And if you zoomed in on one little section anywhere, it doesn't really matter what region we're looking at. I'm going to talk about universal principles. When you zoomed in that, the first thing you'd see is layers, right? You see layers of cells. And depending on who's counting, you get different numbers. I'm just going to talk right now, there's 4 layers. There's layer 2, 3, there's layer 4, layer 5, and layer 6. That's sort of the basic starting point everyone sort of agrees to. And so that's the first thing you'd see if you looked under a microscope. If you then dig in closer, and this was much harder to determine, so here's the same thing, but now blown up, there's another structure which is going on here called mini-columns. And this was controversial for a while, but I don't think it's controversial anymore. There's pretty much universal evidence for it. But essentially, the neurons themselves, these are like the little neurons, they are aligned in these very, very skinny little vertical columns. They're 30 to 50 microns wide. And this is something that happens during development, but it also is true through your life. There's a lot of evidence supporting this. So this mini columns, and these cells in the mini column tend to have a very similar response property, vertically oriented here. So they're really tied together functionally. And there's been a lot of debate about, it was speculated many years ago that the mini column was the sort of repetitive unit of the cortex. And clearly the cortex got bigger by making these sheets bigger in more regions and getting more columns. I don't think that's right, though. I think the way to look at this is the right the level of organization is to really think about the cellular layer as the unit of cortical computation. And that the mini column, I'll talk about this here. Each layer implements a variant of a sequence memory. It's a variant of our CLA. And so I put them in sequence memory there. You'll see in a moment, it's not quite, well, they're different, but they all basically work on the same principle. This is my belief. And the mini columns, they play a critical role in 2 ways. They play a critical role in how each layer learns sequences. And so if you know the CLA, if you read the white paper, if you know the code, you understand that the mini column basically provides the mechanism for doing high order representations. But they also play a role in tying the layers together. They sort of force the layers to represent similar types of things, which we'll get into further. Okay, so that's first level here. And then the question is, well, what can we say about these layers? Well, we can say a bunch of things. So let's look at layer 4 and layer 2, 3. These would, most neuroscientists would agree that these are generally the feed-forward inference layers. So information comes into the cortex, and the destination, typically go in a feed-forward way, is layer 4. There's exceptions to these. We'll talk about some of them in a second. But remember, this information, which is coming sometimes through the thalamus, doesn't really matter. It's sensor information, but it's also copy and motor commands. Now, I use the word afferent. If you don't know that word, that's a neuroscience term for basically feed-forward information. Because it could be coming from another cortical region. It doesn't have to be coming from the retina or something like that. It could be coming from another cortical region. So this is a feed-forward pathway. And layer 4 gets both sensory information and it gets a copy of the motor commands. That's arriving everywhere. And what I'm going to argue, I believe, is that layer 4 is learning sensory motor transitions. Let me just talk what I mean about that. So there's a little picture of a face here on the right. And when you look at a face, or in any image, any still image, imagine, your eyes are constantly moving, 3 to 5 times a second. They saccade and they fixate and they point. And every time there's a complete change of pattern on your retina. I mean, it's just incredible. It's not like it's shifting. That's not right. It's a completely new pattern. You don't perceive it. You have absolutely no idea that your eyes are moving. And turns out, and this is, even Helmholtz in the 1890s recognized this, if the cortex didn't know that the eyes were moving and how they were moving, it would look as if the world was spinning all over the place. You'd get sick very quickly. So it's somehow basically saying, okay, I'm going to try to learn to make a model of how patterns change given motor commands. And I'll walk through that in a bit of detail in a moment. So I'm going to argue that layer 4 is learning sensory motor commands. Now, this is a predictive memory. If you know this CLA, it's a predictive memory system. It's always constantly predicting things are going to happen next. And it does that through cells that are depolarized, but that doesn't matter from an implementation point of view. There's 2 things can happen. It can make a correct prediction. So a correct prediction means that this model of this thing that it's doing, by the way, I'm talking about vision, but it doesn't have to be vision. It can be any sensory motor thing. It can be move my head, it can be move my body, it can be my own voice. We're talking about just patterns that are changing due to my own behavior. If I can successfully predict what the next input will be, then I have a good model of that thing. And what we want to have happen is we want to have a stable representation appear in layer 3. This goes back to the idea of the HTM, where you've got this, you got this hierarchy and you have stability going up. I now believe it's actually happening between layers. I'm pretty certain of this. But if you have an unpredicted, this layer 4 can't predict what's going on. It says, I can't model this data. Then those changes are passed through to the next layer. So we'll have stability if we have a good model, and it has to be unique. I don't want to just have stability. I can just have a dead thing. It'll be stable. It has to be unique. It has to be a unique representation. But if I can't predict it, I pass it to the next layer. Now, the next layer, I argue, is high-order sequence memory. This is what we typically think of as our current implementation of the CLA. Our current implementation of CLA does not know anything about motor. It's just a pure high-order sequence memory. And an example of that would be the following on here on the right. If I learned 2 sequences, A, B, C, D, and X, B, C, Y, just think of like melodies or words or something like that, or just abstract patterns. You notice that BC is part of both of those patterns. And so the question I want to do is I say, well, if I show you ABC, I want to predict D, and if I show you XBC, I want to predict Y. And so that makes it a high-order sequence. It's just like speech and music and everything else in the world. It's actually high-order sequences. So, and so you have to have a way of doing that, and of course, we know how to do that in the CLA, which is, we basically build these unique representations for inputs and context. So these two things, this idea that you can learn the sensory motor transitions, which are not necessarily repeatable high-order sequences. And make that clear. When you staccato over face, you don't always do it in the same pattern. It's not a repeatable sequence. It's not always, you don't always go eye, nose, mouth, eye, nose, mouth. No, you're going eye, nose, blah, 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 all over the place. So that's not a high-order sequence. You can't learn that. But you can, if you can learn to make the transitions from the motor thing, then you have a model for it. Where layer 3 is purely high order. And I believe now, and then layer 3 is the output, essentially, if you want to think about one of the projections up the hierarchy, the layer 3 cells are, it's the next higher regions. So this is going to go on and again. You're going to go layer 3, layer 4, layer 3, layer 4, layer 3, and so on. I believe the following things. So I believe layer 4 is changes due to input behavior. Layer 3 models sequences of the remainders of layer 4. And these are very universal inference steps. These are not specific to any particular modality. And I've come to believe that there actually aren't any others. This is all the brain has to work on. And this applies to vision, touch, hearing, proprioceptive. It all works in all of them. So this is what the brain's got to work on. It does this in a hierarchy, and we'll talk more about the hierarchy in a moment. Okay, so that's what I think is going on in layer 4 and layers 2, 3. What are layer 5 and layer 6 doing? They're a bit more complicated. And I'm going to give a very, very simplistic view of it for the moment. We do know the following, that anything that the cortex generates in behavior starts in layer 5 cells. So that's a fact, and I don't think there's any exceptions to that. So when we talked about the cortex projecting back to the old brain to influence it, it's layer 5 cells. So these are sequences. We're activating many cells at the same time. There's a sparse representation. We're playing back these sequences, activating lots of muscles, so on. So that's a sequence of motor sequences. And then layer 6 is actually 3 different types of things. I'm not going to go into it in detail here, but I'm just saying it's attention. So it has feedback, it has attention, and one other thing. But at the moment, I'll just say it's attention. It does some other feedback things. And the point is, these are both downward projecting things. And attention is kind of like a motor sequence. It's when I talk about attention, I'm talking about covert attention, which is like you looking at something and you're attending to part of it without moving your eyes, or you're tuning into hearing, listening without, sort of tuning out your vision, things like that. So you got these 2 basic, I think this would be a bit uncontroversial. Layer 5 and 6 are basically feedback. Layer 4 and 2, 3 are basically feed forward. There's a lot of other things I'm not telling you about here, but I keep saying that because of the neuroscientists in the room. And I'm going to say something you might be surprised, but over on the right here, I'm telling you my confidence level that I know how to build this. Okay, not that I understand everything going on in neuroscience, but I know how to build a working version of this. And I know how to build a working version of layer 3, layer 2, and 3. It's well understood. We've tested extensively. I'm very confident I know how to build the sensory motor transition memory. I put in 90% there. We've just started implementing it, and we hope to test that extensively this year. I think I understand maybe half of what's going on in layer 5, and maybe about 10% of what's going on in layer 6. But I think I got some of the key components, and I think we're making progress. Things are falling into place. So I'm just giving you sort of a lay of the land here. This is not a typical academic talk. You don't go and say, hey, I have no idea what's going on here. But I also being very bold, saying I understand those other things pretty well. That's a pretty broad claim. Okay, now I think I've already talked about this. Our existing CLA is what I would think of layer 3. When we were developing it, I was thinking of it as layer 3 cells. It has almost all the connections between those cells are within that layer. That's how it works in the CLA. That's how we tested it for. And then what I think is going on here, as I said, layer 4 is essentially the same CLA, but we're doing a slightly different thing. Instead of just feeding connections to itself, instead of just being an auto-associative memory, we're actually providing sensory context. And I've worked this through on paper a couple different ways to make sure it works before we started implementing it. I'm not going to walk you through it here today. I actually have some slides on it, which if someone wants to, I'll go back to it later, but I'm going to skip through them right now. This is a little thought exercise I did. But if we have time later, I'll come back to that. I'm sorry about that. I meant to take it out. So now let's talk about layer 5. And I said it's generating motor commands, right? And it's predictions of the old brain. So now I'm going to switch a little bit here. I'm now going to do some slides I did at the last hackathon. So these are slides, everything up to now is just recent slides I did. Now I'm going to switch to some slides slightly different looking from we did from the old hackathon. And I'm going to talk about how you think about how does layer 5 learn to generate behavior? What does that mean? So let's just do that. So I'm going to, again, start back a little bit. And now here I'm showing a picture where it's going to be a little bit repetitive. I apologize for that. Here we have something where we have a sensory organ and we have a very simple memory. It's like our one-layer CLA high-order sequence memory here. And if I expose that to some dynamic something in the world that's moving and changing, it can learn those patterns. It can learn what's going on in there. And that's basically what we did with Grok, our product. We basically feed it server data, metric data from servers, and that stuff is changing all the time. So this thing doesn't need any behavior. It's just, hey, I'm looking at the changes. It's like an ear. It has no behavior. And we can learn these, and we can do an amazing job of deciphering the patterns and learning the patterns in this thing. That's one extreme. Basically, no behavior. You're relying on the world to be dynamic. The other side of it is, let's take the opposite side of the world. Here I have a structure thing, a house or a room or a building or something like that. And I have an organism with a sensory organ, and I have the little CLA attached to it, but it can't move. And so there's no changes going on in here. There's a lot of structure here, but there's no changes going because this thing's not moving. And so this thing is flatlined. It's dead, right? So how would we learn the structure in this place? Obviously, if I need some sort of behavior to learn this structure, I have to move. I either have to move my sensors or move my body, which are really the same thing. So I have to like move my eyes or turn my head and walk, or I have to lift things up and open them. I just have to have some sort of behavior, and now I can discover the structure of a static world. It doesn't, the world can have structure, but it's not moving. It gets back to my layer 4, layer 3 thing. So again, this is a bit of review, what I just told you before, because I had to go back to these old slides. So this is how I've drawn it here. You've got these sensors, you've got the old brain, pre-wired behaviors. These are some of the pre-wired behaviors I just talked about a moment ago. And so now just like I said earlier, we now send a copy of the vision to the copy of the sensory organ to the cortex. Now let's think about this for a moment. I've got this old brain here, like the reptile brain, and it has behaviors. So it's able to navigate through this thing. Maybe it's doing a wall finding thing, or it's got some behaviors. And so the cortex now will see those changes. Imagine if it was a little robot walking through these rooms, and it says, okay, when I get to the refrigerator, the robot either turns left and it sees a sink, or turns right and sees the dining room, okay? The cortex, this CLA will say, hey, when I see a refrigerator, I might go left, I might see a sink, or I might see the dining room. And it would predict either one. It says, when I see the refrigerator, I'm going to either see one of those two things next. However, if I fed it a copy of the motor commands, like we were talking about a moment ago, it now has the information to say, oh, well, if I'm looking at the refrigerator and I know that the organism is about to turn left, I'm going to see the sink. So I can predict the sink. And if I said if I know the organism is turning right, I will predict the dining room. And so it can make much, much better predictions now if it knows what behaviors are being generated by the organism. It still can't do anything. It's still just a predictive memory. It's not doing anything at this point in time. So how do we get it to generate some behavior? How does the cortex control behavior? So here's, I think, the basic idea, and there's a lot of information in this little transition here, so let me walk you through it. We know that layer 5 cells are generating, they have the cells that project back down to here. And what I believe is going on is that layer 4 and layer 5, layer 3 and layer 5, I say layer 4 or 3, but it's really layer 3 and layer 5 are sort of connected at the hip in a couple ways. First of all, layer 3 projects to layer 5 very heavily, but they also share column activations. So just for the moment, think of L5, layer 5, as a copy of layer 3. You've got two things learning the same basic sequences. Two things have learned, basically representing a sensory motor model of the world, and yet now layer 5 cells are projecting down here. Now this is an important thing. Layer 5 associated links to subcortical behavior. What do I mean by that? These layer 5 cells have no idea where they're projecting. They have no idea. They don't know what they mean, right? They're just sending these axons off into some other neural tissue someplace. But the mechanism we use in the CLA, if you're familiar with it, and hopefully some of you are very familiar with it, it's an auto-associative memory. It's an associative memory, and you're linking one sparse representation to another. In fact, you're linking a series of sparse representations to a series of sparse representations. The same thing can happen here. These cells are firing in some pattern which represents a representation of the sensory motor world. These cells in here are generating the behavior, and we can basically associate these patterns here with these patterns here. In fact, a stable pattern here could actually unfold a lengthy pattern here. The point is, this is a learned relationship. The cortex doesn't know where it's projecting. It just says, I'm sending signals down here, and hopefully they will associate, and I will then be able to associate the behavior which I'm modeling in my own cells. It's sort of a recursive thing. I'm building a model of the behavior, and now I'm using that model to generate the behavior. Okay, I'm just reinforcing, going around in circles here. I haven't generated new behavior yet. I've just learned, but I've learned to have these cells, if these cells became active now, they would invoke the behaviors which made this pattern to begin with. They have the ability to say, oh, I've learned what walking is. I now can invoke walking because I have these learned sequences for what walking looks like. That's an important thing. Did anyone get that? Anyone got questions about it before I go on? Not sure. I know, it's a lot in this slide. I apologize for that. I don't have pictures of it. We have a mic here, so we have to use the mic. Sorry.
I'll go first, I guess. So my understanding is that through experimentation, through movement or whatever, the brain eventually learns the meaning of movement and how that relates to what is coming in.
So remember what I said? I said we're starting off with a system that already has behavior. Right? The cortex is not generating any behavior yet. So I'm not trying to explain how the cortex generates behavior. I'm just saying, how does the cortex learn about behavior, and how does the cortex learn a representation that could invoke behavior if it invoked that behavior again? So imagine a child. Imagine in the beginning a child just starts manipulating the world just by subcortically. It says, oh, it starts moving its head and moves its eyes. It looks at mom. These are all like built-in behaviors. Okay, it chews, it swallows, it burps, poops, whatever. And the cortex learns to model that. It doesn't know in advance. When it's born, the cortex really knows nothing. It just says, I don't really know anything. And so it's building a model of these behaviors. And that model is tied to these behaviors. So if the child is crawling, and it builds a model of what crawling is like, now those cells can actually associate link to the cells that are actually generating the crawling. And these cells, if I could invoke these independently, that would cause you to crawl. Okay. Is there a question still?
Yes.
Oh, okay. Let's see.
Using your memory of past experience to learn how to do stuff.
Yes. That was a statement. Easier than a question.
The question is, is the neocortex getting information on the outputs of the motors, or it's actually triggering the motor behaviors? Because if it's just modeling that and sending that information back, is it basically controlling, or is it just mimicking?
At this point, it's not controlling anything. It's learning to control. Okay. Right? Imagine what happens. Some sensory thing comes in. It generates a behavior. Right? The cortex doesn't know about this. But cortex gets a copy of those things. It's just a sparse pattern. It's just a sequence of sparse distributed representation. So there's a sequence that's being generated here, and there's a sequence coming from the sensory organs. And the cortex says, I'm just going to build a model of them. That's all I'm going to do. I'm going to try to build a model of them. And so that's what the CLA does. It builds a model of these patterns. And now I'm just going to say the cells that are active during these are very sparse representations. The cells that are active during these patterns are being projecting down here, and they're forming synapses with the distal dendrites of these cells down here. Basically I could talk about the mechanism, the biological mechanism for those who want to know it, but it basically saying, I'm going to try to learn to get you to have the exact same patterns here that you had when I learned it. It's sort of circular reasoning. I'm going to model what you're doing, and I'm going to learn how to, send my model down there so I have a connection between the model and the actual thing that's occurring. So information comes in, generates behavior, this guy gets it, it's learning a model of it, and then after the fact, it says, okay, how would I have generated that, could I have generated behavior on my own?
So does it know when it's altering the...
No, it doesn't know. Nothing in the brain knows anything. What'll happen, you'll see in a moment, no, at the moment it doesn't know. At the moment it doesn't know if it's successful. For example, I've given you several examples of things that are really subcortical, really obvious, like breathing and swallowing and things like that, which are totally non-cortical stuff, but you can learn to do it with your cortex. There's other things, like hiccuping, for example. You can't force yourself to hiccup. And the reason is, I believe, is you have a model for hiccuping in your brain, in your cortex. But the cells that know something about hiccuping just do not project to the part of the brain that hiccups. And so it has no way of controlling it. And, like I can't control my heartbeat. I can't control my hiccuping. There's things you just can't control because if these connections don't potentially exist, it just won't be able to do it. But if they do potentially exist, I'll be able to sort of take advantage of that. Let me go on, unless it's a dying question. No? Okay. This is going to get worse, I'm afraid. So the question is, why have a layer 5 in addition to layer 3? I told you layer 5 is almost the same as layer 3. Why would you have a separate copy? Why would you need 2? Why don't I just take the layer 3 cells and project them down here? Well, there's a good reason for that. Everything okay over here? Okay. You need to be able to separate inference from behavior. You need to be able to generate behavior sometimes before you actually sense it. It gets back to the question we just had a moment ago. So think about it this way. In the inference world, like, okay, inference is, patterns are coming in, pre-wired behavior is happening. So you go from layer 3 to layer 5 to old brain. The old brain learns the associative link around here, right? That's the inference side. But when I want to generate behavior, I don't want to have that. I want to generate behavior before I've heard anything. I want to make my speech occur before I hear my speech, right? I don't want to make it occur after I heard my speech, and nothing will ever happen. So I have to be able to generate behaviors before the inference layer actually infers that they occurred. So I have to separate them. I have to have 2 ways of doing this. And so the layer 5 generates behavior before the feed forward inference. It gets confirmed after it happens, but I need to be able to separate these 2 things. Others, you just wouldn't be able to generate behavior. Now, if you're okay with that, then I'm going to go into some more detail about this. Yes, Chetan.
What would the difference, after some training, what would the difference be between layer 4 and layer 5 in terms of how they look? Would they look different in terms of the connections that formed, or what that?
Well, we say before training. We're talking about after training. This, for the moment, right now, this stuff is independent. I mean, these connections 4 to 3 and 3 to 5 would occur the same regardless of whether this stuff happened here. So I don't care if this trained or not, right? But a lot of things would happen up here during training, right? First of all, I have to learn the layer 4 motor changes. I have to learn the remainders of that in layer 3. I have to train layer 5 to be similar to layer 3. So all that has to be learned. But this thing right now, since this guy is not, until this generates behavior on its own, it's really not changing the feedback loop. It's just setting it up. It's setting up the situation so I can generate behavior.
Yeah, and then after it sets up the feedback loop, and now layer 5 is generating behavior in the loop.
It's ready to.
It's ready to.
I haven't shown it doing it yet.
Okay.
Right. All I've shown it's right now. It's just basically copying layer 3. It's saying, hey,
Okay, so then you're about to talk about.
Well, a little bit. We're
Okay.
getting into the harder stuff.
Back to that later.
Right. But I think this general idea, is correct. The general idea is that you always have to think about the cortex or any neural tissue doesn't know anything. And the cortex actually is very, very generic. It doesn't come like, pre-wired to do exactly these things, where these old brain things are. So it has to learn everything. It has to learn what it's representing. It has to learn how it might control what's happening to it. These things all have to be learned. There's no question about that in my mind. Okay. Yeah, question?
A quick comment. What we see, like in the neuroscience field, is that the cortex actually seems so we do a lot of experiments with mice, for example, and the easy behavior. So the mouse has to do something really simple, even if the cortex is lesioned or blocked or inhibited, it doesn't really change.
Yeah.
But the more complex a behavior becomes, so the mouse has to integrate different features, some, behavior, it's running, it's not running. The more it seems to be that the cortex, because of its multiple layers, multiple different cerebrocortical areas, becomes to be involved. So it seems to be that it's kind of a feedback loop that makes actually the signal better.
Well, I would say the following. Maybe you're right. I would say the following. I say the mouse has a really good brain like this.
Yeah.
Right? Well, it's as good as a mouse brain, right? Whatever they do, right? So, and I've heard this too from many neuroscientists. You can ablate the whole visual cortex and you can barely tell the difference. Right? So the mouse still runs around and does the same thing and other things it does, and it has some very subtle changes. So the mouse has a very well-developed old brain and has a very small neocortex, and so the way I interpret that is like, okay, well there's nothing wrong with that. That's just the way it is. Where once you get to primates and so on, the relative ability of this has declined and the size of this has increased dramatically, so we're really relying upon this. I'm not sure if that was a question or just a comment or just more of an observation. I think it's consistent with what I'm talking about here. I mean, yeah. As humans, a lot of mammals have a really, robust old brain at birth. They get up, they start running around doing all kinds of stuff. I think the evidence is that humans, we don't learn to walk. We actually know how to walk genetically, but our brain hasn't finished developing when we're born. So it has to finish developing. It's not like we learn how to walk. We know how to walk. It's just the brain hasn't finished developing itself yet. So it's just like a zebra gets up and starts running in an hour. We would do too if we came out fully formed. Okay, let me just dive into this another layer of detail more. A couple layers of detail more. I'm just talking about hierarchy a bit. Hierarchy is very difficult to grapple with all the time. And what I'm going to argue here, of course, I'm just showing like one small region of the cortex. And in mammals, we have a hierarchy. In mouses, hierarchy is pretty small. Monkeys got like a dozen levels, and humans, they don't really know, but it's quite big. And so I'm just on one little region here, and I really haven't walked through how that region works in detail, because that's like CLA theory. But how would the hierarchy be consistent? So let's say everything I just said existed. Now, we know that one of the feed-forward pathways to the next level in the hierarchy, this would be the next region up in the hierarchy, is from layer 3 cells, and they're going to project up to layer 4 and then to layer 3. So that's your sort of one of your feed-forward pathways, so that's pretty cool. We come in, we have sensory information come to layer 4, to the layer 3, then to 4, and then 3, and 4, and 3, and so on. There's a second pathway coming forward in the cortex too. There's two major pathways that could feed forward. The second pathway are these layer 5 cells, which are generating the behavior. They split, and the axon literally splits in two. The axon goes up and projects also to layer 4 of the next region. This has been very well documented by lots of people, but Sherman and Guillory have been the two guys who have been pushing the importance of this. This, as you can think about it, is also a copy of the motor command. It's a copy of the motor command being generated by this region, right? This region sending this motor command down to here. It's a higher level motor command, but a copy of that gets sent up here. So this is a high level representation of this, like a stable invariant representation here of what it can represent. It goes passed up. This is sort of the high level motor command being passed up. And so it's mimicking what's going on here, right? Here's sensory data plus motor commands. This is sensory data or inference data or afferent data plus motor command. Same thing going on. Now we have a layer 5 up here, doing the same thing as we have layer 5 here, and this guy has cells in it. And where do these cells project? These cells project also back to the old brain. So if you go up like from B1 to B2 or A1 to A2, anywhere you're going up in the hierarchy, especially in the first several levels in the hierarchy, you find that these layer 5 cells are projecting back down someplace subcortically. Now that might seem a little odd. You might think, well, why doesn't layer 5 cells project down to this guy? Why is it projecting all the way to the bottom down here? This is the way it is. This is the neuroscience, so we can't argue with that. One thing you realize that I've shown this as one block here. It's not really one block at all. It's a hierarchy of stuff. It's spinal cord, it's brainstem, it's basal ganglia. Even like if I go into superior colliculus, which is moving the eyes, it's the hierarchy itself. So there's a hierarchy of behaviors down here, and if you look at the connections, they kind of map to the hierarchy up here. The higher up you go, the higher things they project to down here. So this is representing higher level concepts, things that would be higher level motor behaviors, and these are hierarchical as well, and so it's playing off the hierarchy of the old brain doing that. Now there's another thing which is going to go on here, in general idea, as we go in this direction, as we go up the hierarchy, starting down here and then the first level in the hierarchy, second level hierarchy, we're getting this increasing invariance. We're getting this faster changing here and slower changing up here because we're coalescing these sequences as we go up. And so this guy here will be a slower changing patterns than this guy here, and this will be slower changing patterns than this guy here. There's the primary feedback pathway. I've just shown it here. And it starts in these layer 6. It's one of the other layer 6 cells, basically. And it projects back down to the region below it, or several regions below it. And it spreads very broadly across layer 1, actually, of the region below. So you're taking this representation of something happening here and spreading it down here over a large area. And this, of course, is going to be more... I just put new batteries in this. There's something else wrong with this. This is going to be more stable than this, because this is coming from here. This guy is going to be representing the names of these sequences or something like that. So this is going to be a more stable representation, and it's putting it back down here. And you say, well, what's that all about? These are massive connections, by the way. There's a huge number of these coming back. Sometimes they argue there's 10 times as many going back as going forward. We'll want to talk about that in a moment, what that's going on. And then this whole thing is repeated over and over again up the hierarchy. So we're not going to go any further about it. But the point I wanted to make about here is there's a parallelism that's going on. And what's happening at the first level is happening at the next level, happening at the next level. And so if we really, truly understand what's going on in one region, we'll have a really good idea how the whole thing works and how any region is going. And this is all neuroscience. This is not really speculative, this sort of connections here. I didn't show all the details, but I left out the thalamus, but it was too hard to explain. All right, I now want to go in one more level of detail, and we're in very speculative range here. I'm just being real honest here, very speculative, but this is where our current thinking is, and this is where where I'm currently coming out of this. I spent a lot of time thinking about this stuff. So let's go back to look at our slice here again. You got our mini columns, you got our layers. We've already talked about some of these things. So we said, okay, remember we have this sensory data and this afferent data, and the copy of the motor command is going into layer 4. That's what we saw before. And then we know that layer 4 projects to layer 3. Again, I've argued that's going to be stable representations in layer 3. And so that's pretty cool. But what else? Something that's in the literature, everyone knows, but people just don't talk about too much. There are nearly as many connections from these very same fibers going to layer 6. These are very heavy connections. So when this input comes in here, it's actually going to layer 6 too. It sends a little like what they call en passant synapses. They make a lot of connections and they go up and terminate in layer 4. And it turns out that the layer 6 cells, their primary influence is on layer 5 cells. That's interesting. There's a little parallelism going on there. And if I just wanted to say there's ways that people characterize the receptive field properties, and they typically do this in V1, but they do it in other things too. I'll just say that these cells here are what you might call simple cells, that's the term they use, and these are more complex cells, and so those are very well characterized. But again, if you look in the literature, they'll say that layer 5 cells are complex cells and layer 6 cells are simple cells. They have simple cell response properties just like layer 4 does, and layer 5 cells have complex cell response properties just like layer 3 does. Now we know that layer 3 cells project up to the higher region. That's our feed-forward pathway we talked about in a moment. We know that these layer 5 cells project subcortically to the motor areas. But we also know, as I mentioned a moment ago, that these split and they send the copy of the motor command up to the next higher region. So there's a little parallelism going on there as well. And now we're going to jump into the next thing. Now, we look at the actual cells in layer 3, these little pyramidal cells. There's lots of them. There's tens of thousands, cubic millimeters, like 100,000 or something like that. But these cells, the predominant ones you see in layers 2 and 3, they have what are called apical dendrites. And those dendrites, so they have a lot of connections locally, many, many connections locally on their basal dendrites. That's what we model in the CLA. But they also have these apical dendrites, which are kind of like an extension of, it's like more dendritic structure up here. And they send those up into layer 1. That's where those go. Layer 5 cells, the ones that are generating this motor behavior, do the same thing. They're bigger cells. I just took the same picture and stretched it, but they're bigger cells, but they also send their apical dendrites up into layer 1. That's, again, a parallel structure going on there. And then now I'm going to show you, again, layer 1, which I did not label. This is that pattern that's coming back from the region above. there's a couple other sources, but let's talk about that one. And this is that stable representation that's going to be stable while these things are changing. It's going to be more stable than these guys. And that spreads across layer 1 and intersects all these apical dendrites here. So all these cells here and all these cells here reach up into layer 1, they can make connections with that. So you see there's a lot of parallelism going on here. It's almost like layer 5 and layer 6 are doing the same thing, or excuse me, 6 and 5 are doing the same thing as 4 and 3, but these are for feedback and motor control, and these are purely feed-forward sensory going forward, and they both get these massive connections in layer 1. What is going on here? I'm just going to state it. I didn't have time to make pictures of this. I'm trying to come up with ways of visualizing this, but I know exactly, I think I know exactly what's going on here. Imagine I put a stable pattern up here, and then I ran through a whole bunch of sequences in layer 3 and layer 5. So I'm learning these temporal sequences. Now, again, if you know the CLA, what does that mean? I got a sparse representation of cells that, as a unit, represents something. Individual cells don't tell you much. And then I have another sparse representation, another sparse. So a sequence is going through these sparse representations. Boom, 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 boom. That's a sequence using the same cells over and over again, but every representation is sparse. So I'm going through that. So at any point in time, there's a very sparse activity of cells in this layer, and any time there's a sparse activity of cells in this layer. And they're going to get associated with these connections coming back here. They're going to basically, we're going to form connections here in the same way we form connections to the lower brain regions. They're going to say, if I hold this steady while these things are changing, I'm going to form synapses here so that I can invoke all those cells at once. I will make all those cells at once. And when I say invoke them, we're just going to depolarize them. We're not going to make them active. We're going to make them in a predictive state. We're going to send but the neuroscience would be we'd send a dendritic spike and we'd depolarize the cell body. It wouldn't be sending a spike out of the cell, it's just to put the cell in a predictive state. So essentially now I will be able to, basically a single pattern here would be invoke a union of many sparse states. Now if you've heard my other talks about sparse distributed representations, you can form a union of sparse representations and not get confused. And the sparser they are, the more things you can put in that union. You can put hundreds of you can form a union, meaning you OR them together. You can take a sparse pattern, another sparse pattern, another sparse pattern, all in the same cells, and you can invoke all of them at the same time, and it won't get confused, because they're sparse. And so you can invoke a union of sparse states in multiple sequences. All right? So try to imagine this. Imagine layer 3 cells and layer 5 cells have learned lots and lots of sequences. They've learned hundreds of thousands of transitions. So like learning lots of melodies. And now I've run through those melodies while this thing is stable, because that's what's going on. It's stability in the hierarchy. Now when I basically put this pattern down here, I'm invoking every note in every melody that is under this umbrella, under this higher umbrella. It's not everything that this thing has learned. It's everything that's been learned while this has been stable. And so I've been able to invoke a union of all these things. It's sort of like saying a union of motor behaviors or a union of sequences of inference. And this is like, you can think of this as a goal. If I was thinking about a motor behavior, it's like, imagine the following thought experiment. I want to tell this robot or this person to go to the refrigerator. And I've learned 5, 6 different ways to get to the refrigerator. I can go this way, I can go that way. If I'm in this room, I can go here and that room, right? And now I've basically learned all these different sequences, and now I put something down here and I say, go to the refrigerator. And I invoke all those sequences at once. And what happens next is the following. I actually wrote about this in Unintelligent. You're going to get a feed-forward input. So imagine I'm in the house and I've been told, go to the refrigerator. The feed-forward input tells me where I am right now. It says, oh, you're in the dining room. And what it's going to do, it's going to uniquely invoke one element in one of those sequences and says, oh, given I'm in the dining room, I know what pattern to follow to get to the refrigerator. If I was in a different spot, it would immediately select a different sequence. I know what I'm going to do to get to that. So I don't have pictures to describe all this, so I'm just going to leave you the fuzzy concept about it. But I've worked it through on paper. It's an ability to basically tell the unit below you, here's a whole bunch of things that you might do to achieve the thing I want you to achieve. You choose which one based on where you are right now. And given where you are right now, it'll automatically select one of those things and follow it out through time. So it's like a goal-oriented behavior. And the same thing is happening in layer 3, which is essentially saying, here's what I'm expecting you to infer. Here's what I think you should be seeing now. So you're going to have some ambiguous inputs, but you'll see them immediately. Given you're looking for an elephant, I'm going to tell you immediately that input's going to tell you it's an elephant, as opposed to it could be, a gray Peugeot or something like that. So that's the most difficult slide I have here, and I apologize for not having more details, but I warned you this is a very speculative talk, and it's very sort of in progress. So what's our goal? I have a short-term goal, meaning a year or 2 years, this year hopefully. I want to build a one-region sensory motor system. That's the thing I want to do. I want to build a very simple, like our 2048 column CLA. I want to add layer 4, and I want to add layer 5. That's basically tripling the amount sort of what we do today in software. I want to hook it up to some simple thing that has behavior, and I want to be able to prove these concepts out and get them to work as I expect them to work. I have an hypothesis, which is that the only way to build machines with intelligent goal-oriented behavior is to use the same principles in the neocortex. I can't prove that. That's been my hypothesis about machine intelligence from the beginning, which is like, you know, you have to understand how the brain does this. Not everyone believes this. There's a lot of people who don't believe this. But this, I believe this very strongly. And so I think if we want to get to building intelligent goal-oriented behavior and intelligent machines, which you're really going to have behavior to do anything like what's going to classify as an intelligent machine, you're going to have to understand these principles well enough to build them. I should point out, and I usually mention this someplace else, but I didn't mention it today. When I think about building a goal-oriented behavior system, I'm typically not thinking about a robot. I'm thinking about something more virtual. Because behavior can be any way you move your sensory organ through something. It's any sort of change of your sensory organ onto some other different data stream. So I could have a smart bot on the internet, for example, that has behavior and it has no physical appendages. It's moving, instead of being a wall climbing web bot, it could be a smarter web bot, something like that. So you don't have to restrict yourself to thinking this is a physical robot or an arm or a leg or something like that. It could be anything that has behavior. Anyway, this is what we're trying to do. This is why I believe we're going to do it. I believe many of the principles I just talked about have a decent amount of validity to them. Some will certainly be wrong. We don't know yet, but I think we know enough to start building this stuff. That's that. Thanks. All right. I'm happy to take questions. Anyone who wants to leave, you can leave too. I won't be bothered by that.
Pass the mic, please.
All right. We're going to, because we're streaming this and we're recording it, so Matt's going to make sure we have the mic. Is it on?
Is it on?
Yes, it's on.
Sounds on. Thank you so much for the talk. I have a question about the immediate sensory motor system. What plane are you thinking about building it on? Because mathematical is the one that makes the most sense to me, but what planes are you thinking?
I mean, how would we actually test this? I mean,
so what would be the behavior, right? Mathematical functions such as adding numbers, subtracting numbers is a very easy behavior for a computer to replicate.
Behavior. I mean, like what kind of behaviors would you want to exhibit?
Yeah, mechanically, not goal-oriented, but mechanically.
Well, it's funny you mentioned mathematics. That's the last thing I would think of.
Really? Why?
Well, I start with very simple systems, and I think of mathematics as a fairly high-level system. I mean, if I were to build a robotic system, I would start with the simplest thing I could, like, you know, something with 3 behaviors and 2 sensors and, you know, in a limited world. I mean, you got to start with very simple things, or you'll never figure out how to debug this stuff. And then if I want to do something beyond that, I mean, the first things I'd implement, I would do things that, well, you mentioned mathematics. I don't know how to answer that question. I mean, you're not saying mathematically derived testing this. You're not saying testing this formulaically. No. You're saying actually have a behavior which is mathematics.
Exactly. Mathematics can be made very discrete, which is conducive for simple sensors.
But I think you don't want to do discrete things. You want to do things which are not discrete. You want things which are really messy and difficult. I'd rather do, you know, a little, you know, maze-crawling robot that had to deal with all kinds of noise and ambiguity and weirdness in its world, and you know, where the sensory data is never consistent. That to me would be the right thing to do. It's easy to come up with solutions on very, very precisely defined problems. It's tempting to fall into engineering answers to that. But you really want to come up with a solution that's memory-based. It's dealing with the fact that the sensory data is never exactly the same. And the solution to the problem, even though you're trying to achieve something, you never achieve it exactly the same way. So I don't know if mathematics fits that. If it does, you could do it that way. But I don't know what I would do, but I would look for something that has the hard aspects to it. A simple system that solves the hard problems. That's how I would look at it. Yeah.
Hi. So in that same thread, if the system is too simple, is there a chance that the system won't learn or won't? You know, if there's not enough noise or not enough complexity in the sensory environment, is there a chance that the system may not?
Yeah, I don't know.
Not learn much.
I don't think so. Look, our current CLA is 2,048 columns, 64,000 neurons, and we've been testing the heck out of that, and we put it in our product Grok, and it's a very capable thing, and it can do some amazing stuff and learn a hell of a lot of stuff. So that would I consider sort of a minimal system. I wouldn't want to get smaller than that because you start losing the benefits of sparse representations. Yet at the same time, I found that was very, very rich environment. There was no question we could tax this system extremely well for all kinds of problems, all kinds of sequence problems, and so on. So I think you could build a system that is, when I say simple, let's say a layer 4, layer 3, layer 5, each with 2,048 columns, that would do some amazingly difficult things, although in the end result it's not going to be a human, right? You know, it's going to be something simple, but it's going to be solving hard problems. I'm more interested in proving out the theory and solving hard problems and getting it all right than I am in building something that's super, you know, impressive at the moment from a, you know, like a commercial point of view. It's more important to get this stuff right. So that's our attitude. And at the same token, once we think we got enough of it, we'll try to build something useful out of it. So if I thought, you know, I thought of what would I do practically with it. You know, again, our product Grok learns about, it detects very subtle anomalies in data streams. And really, really clever. I'm just happy about how it turned out. You know, so it's doing some really hard stuff. And I could imagine adding behavior to that. I can imagine adding behavior. Like right now, it just looks at certain metrics on servers. What if it could move around and check different metrics and learn patterns between them, or navigate across server structures and things like that, looking for anomalous behaviors with a behavioral aspect to it. That might be a nice way of extending it, something like that. Microphone.
Jeff monitoring the IRC.
Oh, IRC question. Sure. Hi, IRC.
This is from Blue2.
That's Rick.
It's Rick. Okay, he's up 24 hours a day, isn't he?
Yes.
Hi, Hendrik.
His question is, does the future NUPIC that has this sensor motor integration built into it compete with computer science concepts like agent-oriented software and BDI, that is belief, desire, intent model software agent?
Well, that's a good question. I mean, I don't think you could broaden it up and saying, hey, does this approach to machine intelligence compete with AI, neural networks, deep learning? You pick your favorite thing. And this is a subset of that question, I think, Rick is asking. I don't view it as competing. The way I view it is the following. You know, I started with saying we're trying to be a catalyst for machine intelligence. It's not a catalyst for my version of machine intelligence. I want to be a catalyst for machine intelligence. There's going to be one way. There's going to be a way of doing this. I don't think there's going to be 20 or 2. You know, when they started building computers, there was a lot of there were digital computers, there were decimal computers, there were octal computers, there were computers of different architectures, and finally people figured out, you know what, binary is the way to go, and they all settled on that, and the common architectures and so on. The same is going to happen in machine intelligence. There's not going to be 10 different ways of doing this, not even 2. We're going to settle on a couple of common elements. Now, if we all agree to that, not everyone would agree to that, but if we all agree to that, then we'll all have the same goal to get there. Right? My goal isn't to get there my way. My goal is to get to that end point. So well, you think like, for example, deep learning. I think that's great. Deep learning is great. It's got hierarchy. They don't have time. They don't have the issue of, they don't have a sense of motor integration. So let's add those things to hierarchy of deep learning. These should converge. It's not like, it's not a battleground. We should, if we're doing this right, we should all be trying to achieve the same result in the end. So I don't view these things as competitors or alternates. I think, look, there's going to be a couple concepts that win out in the end, and we should be all trying to get there. I argue that if you don't understand the details about how the neuroscience works, you're just not going to get there. So that's my bet. I'm very confident in that. But if I was proven wrong, I guess I would be proven wrong. And so I guess I don't know if I answered Rick's question, but I'm trying to. I'm saying it's not really competitive. We should be all shooting for the same thing. Is that another IRC question or more, Rick? Oh, your question. Okay, and then we'll go to the back.
Your response just made me think of something. Oh, so at the risk of going off on a tangent here, stop me if you want.
I can always stop it if it is.
Is considering computing models and the fact that the current project is basically working on the von Neumann model of computing. Is there you foresee in the future a need or a desire to break away from the von Neumann model?
Yeah. I mean, from a hardware point of view?
Yeah.
Yeah, okay. Let me tell you a couple things are going on right now. You guys may not know this. There's a lot going in this space. First of all, there are some people who are very excited about our algorithms, the stuff I just talked about here with the CLA. There's a team at IBM Alberton under Winfried Wilke who's got, I don't know, somewhere between 8 or 10 people who are working on figuring out how to implement this stuff in hardware, like new device physics, new device architectures. There's a program at DARPA being put together called the Cortical Processor, which is heavily influenced by our work. There's another program at IARPA, which is being put together. IARPA is like DARPA, but for the intelligence community. That's also about discovering new algorithms and so on. And that's, well, anyway, the one at DARPA is about processors, building hardware. The one at IARPA is more algorithmy, but with thinking long-term, you're going to build the hardware. And then there's other projects. There's a team at Seagate who have been looking at our algorithms, perhaps implementing them in flash drives. But then there's generally a lot of people who are interested in neuromorphic computing in general. And so these are people trying to look for architectures to build new hardware implementations of cortical-like circuits. And they're still figuring out which are the right ways to go, and they have different technologies they're trying to apply. All I'm saying is there's a lot of stuff going on right now that you may not be aware of in this field, where there's a lot of interest in trying to find out, like, how are we going to build the hardware that's going to be, 10 years from now is going to be driving all this stuff. So it's going to not necessary. We can only do so much in software. That's why I say I want to start with a very simple system, because I think I could do 3x what we're doing today, but I can't do 100x what we're doing today. Right. And what we're doing today is very, very small. You know that, right? Okay, there's questions in the back. You have to pass the mic back.
Good evening and thanks for the talk. Just if you go back to that slide where you showed the hierarchies between different layers of CLA.
This one here?
Yeah, exactly. So in the white paper, you showed that the thalamus acts as a gate for feed-forward input. How does the basal ganglia, thalamus, and neocortex work together here? You didn't talk about it.
I had that on this slide this morning and I took it out. Why did I take it? Maybe I still have it here. Because I thought it was too much for today. I got all these other stuff I do with these.
One slide deck for
no, I have a lot of stuff.
And I also have another question on top of that.
Let me just see if I have it here. No, I don't have it, unfortunately. What I was going to say is, whoops. What I was going to say, I had it in this slide. It's in another presentation. So this pathway here, the command, copy of the command going forward, that actually goes through the thalamus, and it's gated by the thalamus. I had a little gate here, and that's true here too. And by the way, it's true here too. If, like, when the information comes from your retina before it gets into the cortex, the thalamus gates are right here. So this is LGN, and these are in the pulvinar. But there's a gate going forward, and that's very interesting. One question is very interesting. You had two sort of parts of that question. One is the thalamic gate. And so sometimes this information goes forward and sometimes it doesn't. And I don't really understand it, but it's involved in the intention mechanism. It's clearly, this is a way of saying, I can turn off this information so I do not get a copy of the motor commands, because I'm assuming everything being, it's like if this region is taking care of everything, if this region is understanding everything, then don't send me the details. Just send me the summary. This is the summary, but this is the details. This is like the commands that are being generated. So we can turn that off. And we know a lot about how those thalamic cells turn on and off, and I won't go into it. So that's part of it. There is an intentional gateway, and a lot of neuroscientists believe that that's what it is. There's all this evidence to support that. So I didn't show that here. The other thing you mentioned is basal ganglia, which it plays a big role in here. There's a lot of stuff I didn't talk about. The basal ganglia has another role other than the stuff it does on here. And it projects and receives information from all the different cortical regions. And the current best estimate is that somehow the basal ganglia helps these cortical regions decide which of several motor commands or motor behaviors to exhibit. And maybe some of the neuroscientists know this. There's a lot of literature on this, and I have only read a bit of it. I've only read about 10 papers or something.
There are so many like inhibitory and excitatory circuits.
Yeah, it's very complex. The word basal ganglia basically means lower things. It's not one thing, it's a whole bunch of things, and they just group them all together because they're so damn complicated. But there's a lot known about them. Let's just take a minute. You can get in tremendous amount of detail. What you'll find difficult is finding theoretical understanding of them. You'll find the neurochemistry and the connectivity and the cell types and the histology and all that kind of stuff. But anyway, they do know, and I used to have a picture here, the basal ganglia is receiving information and sending information broadly back, and somehow it looks as if it's helping these regions decide which motor command to do. So I didn't really explain how we do goal-oriented behavior. I only showed some of the mechanism. I don't really know how we do goal-oriented behavior. The basal ganglia is obviously involved in it. He's involved in deciding what the emotional, the saliency of these events are, and so we don't know that. So I'm just trying to build a scaffolding of, like, here's some mechanisms that we know must exist.
And just on top of that, if you look at the neocortex physiology, isn't there like an area that gets activated in particular when motor actions are being held?
No, that's actually you can look at it and you'll say, oh, here's M1, the motor area. It turns out that's really wrong, and the people who originally proposed that will acknowledge that now. We used to think that the cortex is like there's these motor areas, and there still are these motor areas right across the top here. But we now know that every region they've ever looked at has these layer 5 cells that project out. It just turns out that some of them, there's a whole motor area which projects very to the spinal cord, so there's a very motor map, like your hand. You've seen the picture of that, you know, the head and the lips and the fingers. There's a motor map, but it just, even V1, the primary visual area projects to the superior collicus and has a motor output. So it's a sort of misnomer to think that there's a motor area. There's a somatosensory motor area. There's a visual motor area. There's an auditory motor area. Everybody has a motor. We just think of like motor being, you know, moving your arms and limbs. That's a big part of motor behavior, but we also move our eyes when we turn our head, and these things are also, you know, there's other parts of that. So it's true, but it's not true that there's a motor area. Okay. Yeah, go ahead.
So you gave a great example of a goal-directed task that could be, in a sense, one way of, I guess, offering the sensory motor integration tasks by NUPIC or your follow-on incarnations of NUPIC. So I think that's a perfect example of a method within machine learning called reinforcement learning.
Yeah.
To also address this technique or this specific task. I understand that you're also a big advocate for using the principles of the neocortex to address these types of tasks. Is there anything currently in machine learning or reinforcement learning that you see which borrows from those same principles?
Well, so as I understand reinforcement learning, it's very much similar to what I talked about, but it doesn't specify the mechanisms for doing it. You know, it's not a mechanistic. It's more of a concept of like how you would train things, and lots of different ways you can implement it. If I'm wrong, let me know. That's how I view it, right? So everything I've talked about here is consistent with reinforcement learning. I just find, you know, if you read the literature on reinforcement learning, you pick up things, but there's not enough detail in it. The problem is, you know, you don't want to do these really simple things. You want to do this complex thing with constantly changing data and constantly changing sensory streams in a distributed hierarchy. I mean, I want to solve the whole damn thing. And so you can take the concepts of reinforcement learning, which I do, but I'm trying to implement them biologically. And so it's completely consistent. But it's still there. It still leaves some questions. There are things I didn't talk about here because I just don't understand them, and I haven't been able to find them in any of the literature on reinforcement learning or anything else. I could go into them if you want, but I think it's a little bit more than we should try to do right now while we're recording. But so I think again, that's the thing. Like, yeah, I'll take whatever I can from reinforcement learning. It's the right idea. We're actually doing it here. We're basically saying you're learning patterns. You're deciding which ones of those post facto are the ones you want to keep and remember. We're going to take that advantage of that stuff here. And I'm just proposing a mechanism by which how all this can play out. How about we do one more question? Is that right? What's time-wise here? It's 8:20. I don't know if we had a limit to this or not.
We can take a question and then just have conversation.
Yeah, I think then I can take the microphone off and then
close.
Yes, you can close, Matt. I won't disappear right away, so.
Hello, thank you. Have you found any intriguing overlap with control theory or cybernetics?
You know, I read the cybernetics stuff, I don't know, 25 years ago or 30 years ago, and what was it, Norbert Wiener and all that stuff. I just couldn't get anything out of it. I haven't looked at it again in a long time. It was interesting. You know, I read this book by Ashby, you know, Design for Brain. Have you guys seen that? It come from that era. I thought that was really cool, but it just wasn't enough detail in it. It wasn't like, you know, I need to build something, right? We got to build something that's really right. And I felt those things, they didn't give me enough. It's not the way I think, you know.
From a practical perspective, at least the control theory stuff has gone into, it's mostly, you know, process control, industrial stuff, but it tends to deal with time. And that's what I thought was
some of it does. Maybe I should read it again. Very few things deal with time in a sophisticated way. I could be, maybe I missed that. I don't know. Anyway, you know, it just goes back to this premise that I have, and I'll end on this. I just believe you're not going to get there unless you understand how the brain works, how the cortex works. I just don't believe that. And I believe that now since 1980. Yeah, that long. And I haven't been convinced of it otherwise. So, you know, I've been through multiple phases of neural networks and multiple phases of AI and multiple this theory and that theory and this, you know, and where has it gotten us all, you know? So I still believe, and it's just a hypothesis, it's a stated thing, I can't prove it, but the way to do this is you've got to start with these fundamental information processing ideas, sparse distributed representation, distributed memories, local learning rules, and hierarchy, and all this kind of stuff. That has got to be part of your thinking. If I read something and people don't talk about any of that stuff, then I usually say, well, I don't think it's going to get me there, and what can I learn from it? But that's just my bias, and I'm going to stick with it until proven otherwise. And so I'm getting too old probably to change now. So, all right, we're going to end it there. Matt's going to finish up. You want this microphone? You're good. You want to stand in front of the camera?
Thanks, Jeff. Yeah, I guess so.
There you go.
Thanks, Jeff.
Thank you for coming. If you don't know me, I'm the community manager of the Numenta platform for intelligent computing. I just want to emphasize one of Jeff's subtle points is that this is just the beginning of real machine intelligence based on neocortical principles. And we're building it right out in the open in an open source project. Numenta's been building it for years. And we've taken all of that and just thrown it out for anyone to help with, and we're working on it continuously in the open with community members. This is my invitation to you, it's part of my job, to try and get more people to come help us do this. If you're interested in working on this, you don't have to be a neuroscientist, you don't have to be a machine learning expert. I'm not, and I'm helping out. There's a lot of things you could help out with, so go to numenta.com. There's a section about our community. You can find out how to contact me and get involved. I'd be more than happy for you guys to try and help out in any way you can. So thanks for coming. Thanks for your interest. And oh gosh, yeah. There's a lot going on in the NUPIC community right now. I'm a bit overwhelmed. We've got a hackathon coming up in May. This will be our 3rd hackathon. They get bigger and bigger. So we've already got 44 or 50 people RSVP'd for this one, which is almost what we had last time, and it's another month or so in the future. It will be here. So this was somewhat a trial for me to test out this space. It should be a lot of fun. It'll be sort of the same format as we had at the last hackathon. A lot of you were there. I see some familiar faces. Last one was a great event. You can see a blog post about it on numenta.org and see what other people built at the last hackathon. Some really interesting stuff that motivated us to continue to work on the project and see how we can push the boundaries of this technology, how we can do new and interesting things. That's what it's all about, innovation and community and building towards the future. We also have a summer project called Season of NUPIC, where we're trying to assign people that want to work on NUPIC and these concepts with mentors from people within our community already that want to help people work on concepts. So it's a kind of a way to gently lead people in and guide them to completing something that could get contributed back into the code base and help the project. So we're trying to push the boundaries. We're trying to get people involved. If you like this stuff, if this is exciting, please join us. It's a lot of fun. Thanks for coming, Jeff. Thanks all of you guys. Have a great weekend. Just hang around. We'll be here for a little while, so hang out and have some food, and there's beer in the coolers. Yeah, if anybody's here from Pinger, thanks. Oh, it's on the That's right. Thank you, Pinger, and thank you for the hackathon space.